So welcome to the blockchain session. We're going to have 3 talks in this 1-hour-long session. The first one will be given by Yu Shen from the University of Edinburgh. He will present joint work with Angelos Kiayas and Nikos Leonardos on ordering transactions with bounded unfairness. And please, you take it away.
Yeah, thanks for the introduction, and hi, everyone. I'm going to present this paper, Ordering Transactions with Bounded Unfairness. So in this paper, we consider the state machine replication problem, where you have a set of servers, and some of them can be corrupted, and they continuously take transactions as input, and then they want to output an increasing log of transactions. So you can, for example, think of it like a blockchain protocol. And there are 2 desired properties, consistency and liveness, which asks for the honest parties to output the same log, and also liveness asks for the system to process the new transactions within a bounded amount of time. And there is a 3rd property, order fairness, which is often overlooked in the previous literatures, and intuitively, it asks for the system to behave like an honest central server, which receives and processes transactions sequentially in a first-come, first-served manner. Although we have not yet defined what does first-come, first-served mean in the distributed setting, but our observation here is that blockchain protocols like Bitcoin, it does not provide this security guarantee, because the block producers, for example, they have the full power to choose whether to include a transaction or not, and also they can dominate, to say, the order of the transactions in their blocks. And because of this, in blockchain protocols, especially those support smart contracts, they are very vulnerable to reordering attacks, like front-running and sandwich attacks. So here we have some data on the Ethereum blockchain, and this MEV stands for the value that the adversary can gain from, to say, sophisticatedly reordering the transactions on Ethereum. So actually, you can see that the honest users, they suffer from a huge loss. So we want to mitigate the reordering attacks, and in this sense, we would like to achieve order fairness. And there are 2 ways to think of this property. One is sender fairness. I'm not going to talk about the sender fairness in this talk. We have another paper which is going to appear in a conference very soon. In this talk, I'm going to discuss this receiver order fairness. So here, this receiver order fairness mainly says that you want to output some transaction logs, which we call profiles, sigma, and based on combining all the local views of the honest parties. So it's like you have n transaction profiles to represent the local view of all the honest parties, and you want to combine all of them together into a new one. So here we have a very natural definition of receiver order fairness, which says that if for the majority of the parties they see transaction tx before tx prime, then you order tx before tx prime in the final log. However, the problem is that this very natural definition is impossible to achieve because of Condorcet cycles. And it mainly says that even if the local orders, they are non-transitive, they can be cyclic after you combine them into the global one. So here we have a very simple example. For example, it's like you have 3 parties, 3 transactions. The first guy says transaction 1, 2, 3, and the second guy says 3, 2, 1, and the third guy says 3, 1, 2. So if you consider the majority preference, you will see transaction 1 before 2, 2 before 3, and 3 before 1, which means that they are cyclic, and no order can satisfy the natural definition above. And this is a very simple example. In the worst case, these Condorcet cycles can be, to say, infinitely large. So we need to relax this natural definition of receiver order fairness, and there are 2 main directions. The first one is called timed order fairness, where you want to order transactions if they are sufficiently apart from each other. So here we have transaction 1 before 2 because they are separated by a time tau. However, the downside of this notion of fairness is that we give up on ordering many transactions as long as their dissemination window overlaps. So here, for example, the order between 2 and 3, they are unspecified, even if they can be, to say, ordered very, very easily. And another direction is called batch order fairness. So it mainly says that we want to identify Condorcet cycles and order them in a batch. So it's like there's no order within this batch. And for this type of notion, it has no dependence on the shared notion of time, which is good, but it gives up on assigning the Unix index to all the transactions. Like in the batch, there's no order in the batch, but we want to highlight that for state machine replication protocols, eventually you need to serialize all the transactions, which means that you must decide the order inside the batch. So now I'm going to introduce our notion of order fairness, which we call it bounded unfairness. And this is based on the question that with condensate cycles, we have to order transactions unfairly. We must order transactions unfairly. So can we minimize to say for any pair of the transactions, the number of the transactions between them if they are unfairly ordered? And we are looking at this question because in the state machine replication problem, this gives us a very important security guarantee. If you can bound the number of the transactions between the unfairly ordered ones, then you can also bound the number of the unfair state updates occurring before any transaction. And just to give you an example in the DeFi, so it's like if, when the multiple users, they are interacting with the automated market maker at the same time, and then if we have bounded unfairness, then it can help to minimize the unfair slippage. And just to give you some more details on this bounded unfairness, ideally, we would like to order tx before tx prime. But the problem here is that under some circumstances, we have to order tx prime before tx unfairly. So in this case, we should not order tx prime, so say, too earlier before tx. And this gives us a parametric order fairness notion, which we call it phi b fair order. So here phi is like a threshold, like the majority preference, and this b is a bound which says that when you want to order tx prime unfairly before tx, then tx prime should not be ordered b positions before tx. And here we let b be a function of all the transaction profiles and also transaction tx and tx prime. So here, obviously, the most important thing is to explicitly define what this bound is. But before we do that, let me first give you some more details on this definition. So this is an order fairness definition that is unrealizable if this function b is too small, which means that, for example, you have a condensate cycle, and this b function outputs b for all the transaction pairs in this cycle. In this sense, it is unrealizable because you must, to say, unfairly order at least one pair of transactions. And it is a trivial notion if b is too large, as you can imagine. If b is super large, like almost the size of the profiles, then which means that you can let the first transaction to unfairly precede the last one, which we do not want to see. So our goal here is to explicitly define the smallest possible function b, and I'm going to do it now. So before we proceed, we need to introduce some graph notions. We need to convert the local transaction orders into a graph. And this step is very simple. We call it transaction dependency graph. And what we can do here is that we add transactions as nodes, and if we have majority preference between two transactions, then add an edge. And what we can see here is that the condensate cycles are strongly connected components because they are cycles. And you also have some results on the graph, which says that the larger phi on the bound, then you will not have small cycles. So after we convert the local profile, the profiles to this transaction dependency graph, what we can do here is that, we can see that these graphs are oriented graphs, which means that there's at least one, there's at most one edge between any two transactions because we use the majority preference. And also, a transaction profile is like a vertex ordering on this graph, because if after you order all the vertices, you also order all the transactions. And in terms of bounded unfairness, we only need to care about the backward edges. So what are the backward edges? If you want to order all the nodes, nodes from left to the right, then we only need to care about those edges from the right to the left. And this implies that we order the transactions unfairly. And the most important metric is obviously the length of these backward edges. So we are considering this graph theory problem, which asks for the vertex ordering on a directed graph, which minimizes the longest length of the backward edges. I'm going to show you an example here. We have a transaction dependency graph on the left. And we have two orderings on the right side. The above ordering is somewhat a good ordering, because you can see that in this first ordering, the longest backward edge is of length 3, while in the second ordering, the length of the longest backward edge is of length 7. And we can see that the first ordering has a smaller longest backward edge. And actually, this is the bandwidth optimal vertex ordering on this graph because the directed bandwidth of this graph is 3, which means that you cannot find a vertex ordering such that the longest length of the backward edge is 2. So why this graph theory problem is very important when we want to define the order fairness. So we did some research on the complexity of this problem, and it turns out that over oriented graphs, this problem is still a hard problem. It is NP hard, which means that we cannot expect for the polynomial time algorithms. And also, we explore the worst case of the directed bandwidth. So if you consider all the oriented graphs with n nodes, then in the worst case, the directed bandwidth of the graph is only, to say, logarithmically smaller than the total number of the nodes. But I want to say that although in the worst case, the directed bandwidth is large, but even for some very complicated graphs, they might have directed bandwidth that is very small. And also, as you can see, you can very trivially solve this problem if you check all the vertex orderings, and it takes in factorial time. But if you are smart, you can solve it in exponential time, where the exponent is the size of the edges. And in oriented graphs, the size of, the number of the edges is quadratically bounded by the number of the nodes. OK, so now this dBW means the directed bandwidth of a graph. Now we are ready to define this function b. So what we want to say here is that if we want to order transaction tx prime unfairly before transaction tx, then tx prime should not be ordered before tx for these many positions. For how many positions? Which is defined as the directed bandwidth of the strongly connected component that includes transaction tx and tx prime. So why do we want to define it in this way? You can see that if tx is seen by majority of the parties before tx prime, and we want to order tx prime before tx, for majority of the parties you see tx before tx prime and they are not in the same cycle, then which means that tx must be ordered before tx prime. And in this, we do not need to care about the Condorcet cycles in this case. And if they are in the same Condorcet cycle, which means that they appear in the same cycle in the graph, then in the case that we want to order tx prime unfairly before tx, then this transaction can be at most ordered to say the directed bandwidth of this cycle, that's that many positions before tx. And if we go back to this graph, what we prefer is the first ordering than the second ordering, because in the first ordering we get bounded unfairness. To say if transactions are unfairly proceeded, then that's at most 3 positions, while in the next ordering, it's like, if the first transaction unfairly proceeds the last one for 7 positions, which is unfair for the last transaction. So in our paper, we also show that if you define this B function using the directed bandwidth, then this is the best possible thing that you can hope in terms of bounded unfairness. And especially what we show is that for any other function b, as long as it is, a realizable function b, then this b will be larger than the way that we define it using directed bandwidth. Yeah, and I just want to give you a very quick protocol overview. This is actually a permissionless blockchain protocol that achieves directed bandwidth order fairness, and it's very straightforward. So you use 2-for-1 proof of work to mine blocks and the transaction profiles. I will explain what is 2-for-1 proof of work in my next talk. And then what you do here is that you convert the blockchain to a transaction dependency graph, and you run this directed bandwidth algorithm on all the strongly connected components, and that's all. And the last thing that I want to highlight here is that this problem in state machine replication is much more complicated than what I said just now, because we need to care about liveness. Because Condorcet cycles can be very large, and in some circumstances, you want to guarantee liveness, but there's an ongoing Condorcet cycle, which means that you have to order transactions with partial information of this Condorcet cycle. And this can be problematic. We have some results between bounded unfairness and the liveness. And I just want to show you the one thing. This one is if the transaction dissemination that's asynchronous, then there's no way to expect the consistency liveness and the optimal bounded unfairness. But we can have some relaxations, like to hope for the weak liveness, where liveness is only guaranteed after the to say the ongoing of a very large condensate cycle. And to just very quickly give you a summary, what we do here in this paper is that we define transaction serialization with bounded unfairness. This bounded unfairness is defined by using a graph theory problem called directed bandwidth. And we also analyze the complexity of achieving this notion of unfairness, and we give two constructions. The first, they are both permissionless blockchain protocols. The first one achieves consistency, weak liveness, and the perfect bounded unfairness. And the second one achieves standard liveness, but with, to say, relaxed version of the bounded unfairness. And that's all. Yeah, thanks.
Yes, please come to the microphone if you have questions. Go ahead.
Thank you for the interesting talk. So I was wondering whether you have some insights to which extent this bounded unfairness solves, for example, the sandwiching attacks. Because it seems there it's sufficient to just swap two transactions. So you have some idea?
For sandwich attacks?
Yes.
Yes, so, I mean, we cannot completely solve this type of attacks because we have to order transactions unfairly. But our thinking is that if you have less number of the positions to say front round, then you might be more secure because you have less positions to insert those transactions before you.
Okay, thank you.
Thank you for the nice work and the nice talk. You mentioned the weak liveness towards the end, namely that there can be these cycles that go on forever. Yeah. There is a paper called Themis by Kelkar and others that seems or claims to resolve the issue, and also criticize paper that we had done with the notion that the algorithm is called quick order fairness. We have another notion there called differential order fairness. Do you have a comment on this? What is the state on liveness between these?
Yes. So the thing here is that we can also achieve standard liveness if we just cut the condensate cycles, and in such a way we achieve some weaker version of bounded unfairness. And the comment on that paper is that in terms of bounded unfairness, that paper is not good because it gives you an ordering with very large unfairness in our sense. But
because they could go larger and larger.
Yes, yeah, but I mean, this bounded unfairness, maybe that's not the only way of thinking front-running mitigation. Maybe their protocol can be useful in some use cases. I don't know. Yeah.
Yeah. Okay. Thank you.
Thank you.
Any more questions? So I have one. So based on your slides and the definition you gave, you defined these profiles like party-centric. Yeah. It is like. If I understood correctly, so a fraction of parties.
Yes.
So is it easy to generalize this to like a resource-based model where parties just hold,
Yes. Actually, we use a protocol in the resource model, and we give a definition based on the resource model.
Oh, nice.
Yeah, I didn't present it.
Okay, so thanks a lot to you, and we will see you again at the end of this session for the second talk. And now we come to the second talk, which will be delivered by Søren. And he will present joint work with Chandra Liu Sang and Christian Matt. And the talk will be about their paper on asymptotically optimal message dissemination, also in the with applications to blockchains. And please, Søren, take it away.
Thanks. So yes, to start this talk off, I thought I would dissect the title a bit and start explaining what I mean with message dissemination. So here we care about a functionality, which we usually refer to as flooding functionality. And what this functionality provides is a guarantee that all parties can input a message. And if any such party inputs a message at time t, and this party is honest, then within delta time, it's guaranteed that this message must be delivered to all other parties, right? So a bit more formally, right, that the probability that it is not delivered to all other parties must be negligible. Within this time delta, must be negligible in the security parameter. Right, and here this delta, well, that may be known or unknown. This depends on the underlying assumptions about what channels connects to parties, right? But our construction is independent of this. Okay, so this is the functionality we would like to implement. And what we would like is to implement it in a setting where there exists an adversary. And the adversary we consider is allowed to corrupt any set of parties, but there must be a constant fraction of parties, gamma, that remains honest throughout the protocol. So the state of art when it comes to implementing the flooding functionality in this setting, that is to let each party forward the message just to a random subset of parties, which again will forward the message to another subset of parties, right? So if this is P1, to which the message is input, well, then P1 will select a random neighborhood and forward the message to those parties, right? They in turn will select a random neighborhood as well and forward the message to those parties, and so on, until all parties have received the message. So in such a protocol, we care about performance. And the indicators for performance we're interested in is the maximum number of neighbors. This means the number of parties any party needs to talk to. We're interested in the diameter of the communication graph. So this is the longest, shortest path between the sender. So the shortest, longest path between the sender and any other party. So in this case, for this graph, it would be just 3. And then finally, we are interested in the number of bits that are actually transmitted over the wire, right? So, well, I already sort of gave away what the performance of the state of the art is, right? But there's actually one protocol which beats it with respect to the diameter, right? The very naive protocol that sort of just forwards the message to all other parties, that is actually better because it has a diameter of just 1. But of course, it's not better with the other performance indicators because the party needs to talk to all other parties and needs to submit quite a few bits over the wires, right? All right, so to be a bit more specific, if we look at those type of protocols, which is sort of state of the art, where we just forward to a random subset of parties until all parties have received the message, well, it's shown in those works that the maximum number of neighbors that can be achieved in this way, that's upper bounded by the inverse to the fraction of parties that's guaranteed to be honest, multiplied by the logarithm to the number of parties plus a security parameter. And now, because we send the message to all our neighbors, the entire message, right? This means that if we send a message with L bits, then the maximum per party communication, well, that would just be the number of neighbors times this length of the message. And this gives a diameter that's logarithmic. So our new protocol, which we present in this paper, it has asymptotically the same number of neighbors, but we managed to reduce the per party communication by cutting away this logarithmic factor plus the security parameter. And we do this while retaining the same diameter. Now, naturally, it's not as good as the naive protocol in terms of diameter. But we do present another protocol called EC-cast, which has the same number of parties, neighbors, but manages to achieve this per-party communication, which is comparable to our other flooding protocol, and which we later into this talk will see is actually optimal. And does that while having also a constant diameter with in fact, just the 2 hops to reach any honest party. So before diving into the actual construction in our work, I thought I would take a minute to convince you that this protocol is not only theoretically better than state-of-the-art, it's actually practically better as well. So to show this, we have implemented probabilistic simulations and run both the previous state-of-the-art, which is this fan-out flooding type of protocols, and our own protocol 100,000 times. And then we've sort of reported on the error rate here on the y-axis and on the per-party communication to send a 1 megabyte message on the x-axis. So we see that if you really want that all of the 100,000 runs succeed for the fan-out flooding protocol, then we need sort of roughly 45 neighbors to ensure this. And that, of course, translates to 45 megabytes of per-party communication. Now, with our protocol, we managed to cut this down to 25 megabytes of per-party communication to ensure that all parties in all simulations have received the message, right? and that's for a diameter that is similar to that of the fan-out flooding, namely 5. And that's for all between these 4 and 16,000 parties. Now, if you're okay to increase the diameter to just 7, then we can use this internal parameter of 8 in our new protocol, and this will give us a per-party communication of just 13 to ensure that all parties receive the message. All right. So now, how do we construct our protocol? Well, unfortunately, it has been shown in previous work that both for Aderini type graphs and for fan-out type flooding graphs, one cannot go lower than this amount of neighbors are needed, otherwise we'll have an unconnected graph. So this is kind of difficult to cut away, and we kind of need to come up with a new idea. And the new idea that we come up with, that is, instead of sending the entire message to all our neighbors, we take the message, run it through some kind of functionality, and divide it into more minor messages. We call those shares. And then for each of these shares, we submit them to a new functionality again. And this new functionality will deliver the messages to the parties, right? And what our functionality will guarantee is that at least a constant fraction of shares are received by all parties. Right, and then if we're able to reconstruct from this constant fraction of shares, then we can guarantee that all parties have received the message. So the first functionality, right, that's a pretty well-known functionality. That's erasure correcting / error correcting codes, and can be implemented by for example, Reed-Solomon codes. And if we do this, then if we input a message of length L, then each of these new shares will have a length of L prime, which will be just the length of the original message divided by the fraction of shares needed the number of shares needed to reconstruct. Okay, so all that is left is to come up with a protocol functionality that has a suitable set of properties to deliver these messages to all parties, right? And what we come up with here is called a psi weak flooding protocol. And this gives the guarantee that for each party has a probability psi of receiving any message that is input to this protocol. And now, if we divide the message into at least log of n plus the security parameter shares, then Chernoff, in combination with these weak flooding protocols being run independently, one instance for each party, will guarantee that we receive at least a constant fraction of the shares if this psi is constant. Now, of course, to guarantee this with the same nice properties that previous state-of-the-art has, right? We want this to have a logarithmic diameter. Therefore, this weak flooding protocol, we want this to deliver the message within a logarithmic distance as well. Okay, so now it's worth observing that the per-party communication and the neighborhood of this construction, right, that will be mu times the per-party communication and neighborhood of the weak flooding protocols, right, because we want one such instance for each share. And this means that if we really want this to be asymptotically optimal and be comparable in terms of neighborhood to existing work, well, then we must have a per-party communication. Then this weak flooding protocol must have a per-party communication that is only the length of the input message divided by the fraction of parties guaranteed to be honest, and must have a neighborhood of only that is inverse to the fraction of parties that's guaranteed to be honest. Okay, so this is our requirements for a weak flooding protocol. So how do we now achieve this? Well, we have seen two flooding protocols so far, right? We have seen the naive thing that doesn't work because it has too many neighbors. And then we have seen this fan-out flooding, which is previously considered state-of-the-art, right? And in our work, we proved that fan-out flooding, in fact, is a very, very good weak flooding protocol. So we show that if we set the degree that each party should send, the number of neighbors that each party should send to, this d, well, then it's enough to set this degree to be inverse to the fraction of parties that are guaranteed to be honest. And then this gives us exactly what we need. It ensures that there's a constant probability to deliver within a logarithmic number of, with a diameter, within a logarithmic number of hops. and it ensures that we only have these inverse of the fraction of honest neighbors. And finally, it has the desired property with respect to the per-party communication in terms of the length of the message input. Okay, that's pretty nice. So now we have actually guaranteed that all parties have received at least a constant fraction of shares. Now we should be able to reconstruct. Well, except it may be that there are some shares that did not originate from the original message that are delivered to some parties, right? An adversary could try to inject messages. So we need to prevent this in some way. And what we do is to add a small stamp to each of the messages that was created from the original message, and then we just forward this stamp on all the message rights. If this has some sort of reasonable properties, then it's easy to see, right, that now the parties will be able to distinguish which messages they should use to reconstruct the original message from. And the way we, this stamp, right, that can be implemented by just using, adding a membership proof for a weak cryptographic accumulator to all shares. And an example of such accumulator, right, that could be a Merkle tree. Okay, so that's the protocol. But of course, right, adding these membership proofs and using the Reed-Solomon codes, that's create a bit of overhead compared to just sending the message to all other parties as other work does, right? So how long should messages be before our protocol are actually advantageous? Well, if the message is at least log n plus the security parameter multiplied by the log n plus the security parameter, well, then our protocol is theoretically optimal, which I will get back to in just a minute. And in practice, this means that if the messages are longer than roughly 2 kilobytes, then our protocol will use less per-party communication. All right. So now I have mentioned quite a few times that our referred to our protocol as being asymptotically optimal, right? That's because our protocols have this, that the message complexity, maximum per-party communication is only the length of the message divided by the fraction of parties guaranteed to be honest. Well, of course, this requires a proof, right? And we prove this in our paper. So I thought I would spend the last couple of minutes of the talk giving you some intuition for why that is the case. So consider a protocol execution for some flooding protocol on the left, and now consider the following adversarial strategy. So what an adversary does is first divide this group of this set of parties into groups of size roughly the number of parties times the fraction of parties guaranteed to be honest. And then at random choose one of these sets called cliques, or referred to as cliques, and let this be the only set of parties that are honest after the adversary decided whom to corrupt. Okay, and then the third step is, well, each of these cliques that are dishonest, they will not communicate with any party from the honest clique. They will communicate with the sender, but they will not communicate with any of the other parties. And by communication, I mean I will not receive anything from dishonest parties, from honest parties, and I will not send anything to honest parties. Okay, so if you consider two protocol executions, one where CI is the set of parties that were selected to remain honest, and one where C1 was selected as the set of parties that are allowed to be honest. Now, from the sender's point of view, those cases are indistinguishable. Right? The communication the sender receives is exactly the same. Okay, so this means that if the sender wants to ensure that all parties must be able to reconstruct their message, well, then they need to forward at least L bits, right? They need to forward the entire message to all cliques. And therefore, since there are 1 over gamma of such cliques, well, this gives a message complexity of L over gamma, where gamma is still this fraction of parties guaranteed to be honest. All right. So just to try to motivate you to also read the paper, we have additional stuff in the paper. And the first theorem, an additional theorem we prove in the paper, is that property-based flooding implies UC flooding because there are no secrecy. Then secondly, we also proved that any protocol that is secure in the non-weighted setting, which is the setting we have considered where an adversary is allowed to corrupt a fraction of parties, that can be transformed into a protocol that is secure in the weighted setting, where each party is publicly assigned a weight, and an adversary is allowed to corrupt a fraction of honest weight. And thereby we also achieve asymptotically optimal message dissemination in the weighted setting. Right. So in conclusion, I presented the EC flooding protocol, which is a protocol with a logarithmic neighborhood, a logarithmic diameter, and only this length of the message divided by the fraction of honest parties communication. Then I've presented simulations showing the practical advantage over existing approaches. And then finally, I've shown that this L over gamma is actually an optimal per-party communication. Thank you for your attention.
Thanks. So again, please come to the front if you have questions. Thanks a lot for the nice talk.
Thanks.
Yes, thanks for the talk. I have two questions about the relationship between this and reliable broadcast. Do these flooding protocols guarantee any like completeness or totality properties?
No, they don't. Right, so that's the big difference between flooding.
Yeah.
So flooding only allows and ensures that messages sent by honest parties will reach all other parties. Right, so there's no agreement. It may be that the adversary injects messages, other messages, and there are no guarantees that it will be received by all parties if there is a dishonest sender. So there are no agreement consistency requirements.
Yeah, so it's a weaker.
Yes, a weaker primitive. Right.
But do the lower bounds that you prove then also give lower bounds for communication complexity of reliable broadcast? And do your lower bounds have explicit constants in them, or just big O? Are they just big omega?
So to answer your first question, I think I'll have to think about that. It may be. And the second question, it's only proven in big omega. But I expect that one can, be a bit more specific about this.
There's an open problem that I've been trying to figure out for a while, which is like, just for plain old reliable broadcast, there's a big omega n times L lower bound, but like, what is the actual constant?
Right.
I think it's 1.5, but I don't know how to prove it. So.
That would be pretty cool.
Well, yeah, okay.
Yeah. Thanks.
Thank you for the nice talk, Son. So I have a question. I think you prove in the paper, I think it also is clear from the construction that this isn't secure against a fully adaptive adversary. You can just cut off the communication graph. So I was wondering, these flooding protocols are usually used in in scenario, as sub-protocols to bigger protocols where everybody has to constantly send around messages anyway. So could you restate this or extend this to a setting where everybody sends at the same time, and then you obfuscate the sending pattern so that it is adaptively secure? Because if everybody sends messages anyway, you have all-to-all communication, so there's nothing you can do, but you can hope to get adaptive security.
My suspicion is that it would still be able to cut off some parties from receiving the message, right? Because if you have a fully adaptive adversary, this means that they can see the communication pattern, right? Just before.
No, but you can randomize what you send to where if you encrypt it. It's a technique that I've used myself.
Right. Maybe that's thoughtful, yeah.
But would the lower bound then still hold, actually, or?
I think the lower bound holds against, so I guess there would be some version of the lower bound being against in parallel setting, right?
Okay, yeah.
I'm not sure how that would work out, but yeah.
Okay, thank you.
Thanks.
Yeah, maybe one quick final question.
Okay,
Christian?
let's be quick. Classical protocols are a combination between push and pull. You only consider push/flooding. Why?
Yes. So there has been a lot of classical work on both pushing and pulling, right? And the thing is that when we are in a Byzantine setting, then an adversary can just pull for the message, right? And it's difficult to know whether they are asking because they don't know it or because they just want to increase your communication complexity.
Increase the communication of the honest guys. Okay. Yeah. Well, maybe room for more research.
Yes, I think it is. Most certainly is.
Thanks a lot. So let's thank the speaker again. And we have the pleasure to welcome Yushen again on stage for the presentation of the last paper in this segment. It's about proof of work based consensus in expected constant time. This is joint work he's presenting with Aglos Kyrias and Juan Garay. So please, you.
Thanks for the introduction again. Yeah, and hi everyone. I'm going to present this paper where we give a consensus protocol in the proof of work setting that terminates in expected constant time. And this improves the previous consensus protocols in the same setting, which has round complexity polylogarithmic kappa, where kappa is the security parameter. And we also build the distributed ledger protocols on top of this consensus, which confirms all the transactions in expected constant time. So we are in the proof of work setting where we model the hash function that is used in the proof of work as a random oracle. And the task, to say the problem that we want to solve is the consensus, where we have n parties, t of them are corrupted. Honest parties each have their own input, and what we want to achieve is that honest parties output the same value. And if they start unanimously, the adversary should not be allowed to swing the output, and they should eventually terminate. And in our setting, we do not know the exact number of the parties. So this problem in the classical setting has been extensively studied, and also it was believed that without a PKI, this consensus is impossible when more than 1/3 of the parties is corrupted. Even use cryptography. Then, in an open email of Nakamoto, he proposes a proof of work protocol that solves the consensus problem with honest majority and without PKIs. But the interesting thing is that Nakamoto gives a wrong protocol. It is a consensus protocol with no validity. And in this protocol, Nakamoto asks the miners to generate a blockchain and then switch their input with the longest chain. So the problem is that if the adversary finds the solution first, then even if all the parties start unanimously, it will not guarantee validity. So this is not a consensus protocol. And it is actually in Eurocrypt 2015, in this Bitcoin backbone protocol paper, they give the first proof of work based protocol where parties mine blockchains and they insert their consensus input into the blocks. And when the blockchain is sufficiently long, they just output the majority bit in the prefix. So you have agreement from common prefix and you have validity as long as the corrupted parties controls less than 1/3 of the parties. You cannot have, in this protocol, you cannot do it with honest majority because the adversary has the power to kick out those honest blocks, at least as many as the blocks that they generated. And which means that this corruption threshold is actually suboptimal. And in the same paper, they give the honest majority proof of work based consensus protocol. And I'm going to give you some details. We will use this honest majority protocol in our protocol as a very important building block. So what happens in this protocol is that parties still use proof of work to generate blocks and to extend the blockchain. And they also additionally use proof of work to generate inputs. And they only include inputs which are kind of authenticated by this proof of work. Only this proof of work, the input on the blockchain. And when the blockchain is sufficiently large, then chop off the last k blocks and then output the majority among the unique inputs in the common prefix. So what's the round complexity of this consensus protocol? That's polylogarithmic kappa, because you need polylog rounds to guarantee that agreement and validity happens with overwhelming probability. So we are going to improve polylogarithmic to expected constant. And before we proceed, I want to highlight one thing. So here we have two sub-procedures that use proof of works. And if we naively model them as two different random oracles, then we have the following problem. How can we prevent the adversary from shifting his computational power? So it's like this is a protocol that is only secure if for each party it makes one query to one random oracle and another query to another random oracle. But actually, you have no way to prevent the adversary from focusing his computational power on only one of the random protocol and completely drop from mining another. So which means that in this protocol, we need a primitive called 2-for-1 proof of work. And I'm going to introduce it. So the problem here is that if you have two sub-procedures that use proof of work, if you model them as two different random protocols, that's not secure because the adversary can just join force on one of them. So what we need to do is that we need to bind the mining procedures of these two sub-procedures using 2-for-1 proof of work. So it's like you have only one random protocol query. And if the output has sufficiently many leading zeros, that's a valid block. If it has sufficiently many trailing zeros, then that's a valid input. So in this sense, one random query can be both the success on blocks and the inputs, and they are independent and they are binded together. So the adversary has no way to switch in his computational power. And we are going to improve the round complexity of proof of work-based consensus protocol to expected constant. So let me show you how expected constant time protocol works in the classical setting. In order to beat this T+1 rounds lower bound, we need a randomization. And I'm going to introduce one consensus protocol that's called randomizer king consensus. So here, the protocol proceeds in iterations of the phases until parties terminate. And what they do first is that parties first check if they start unanimously. And if this happens, then they terminate. This can be done by simply setting a threshold on the message and by counting the messages. And if this does not happen, then the side effect of this validity check is that the adversary has the power to let some of the parties terminate in this phase and some of them terminate in the next phase. But if the adversary, he does not choose to do so, then there are honest parties that are still confusing. So what they do is that the honest parties will do this oblivious king election type of things. It's just like a leader election where it runs in constant time and with constant probability, it elects an honest king obliviously. And if this happens, all the parties terminate with constant probability. If this does not happen, then they go to the next phase and hope they are lucky for the next time. So this protocol terminates in expected constant time. And we are going to also use this protocol in our construction. And just to give you a sum up on the background, we are going to do consensus in the peer-to-peer network, unauthenticated, and the public setup with common reference strings as the genesis block. And also we model proof of work as a random protocol. And we want to improve the existing protocol, which terminates in polylogarithmically many rounds. In this picture, that's OK, but it can also be polylogarithmic. So we are going to talk about our protocol. It is a parallel blockchain protocol. And yeah, this is the summary of the setups and assumptions. We are in the same setting as GKR15, also the same setting as Bitcoin with genesis block and the random protocols, and we do expected constant. So this is our construction. What we do is that we want to mine blockchains in parallel, and we bind all the mining procedures using by extending the 2-for-1 proof of work to M-for-1 proof of work, and we set M as a polylogarithmic function of kappa. So let me detail what will happen when you mine the blocks. So it's like for random oracle query, it has kappa bits, and we divide them into M sections. And on each section, if you have sufficiently many leading zeros, then you have a valid block on that corresponding chain. And if you have sufficiently many tailing zeros, then you have a valid input on that single chain. So it's like we run M instances of the GKR15 protocol in parallel. And the important security guarantee is that they are binded using M-for-1 proof of work, which means that they are mutually independent, and the adversary, he cannot gain any advantage by for example, swinging the computational power. So let's think about the GKR15 protocol. It is a consensus protocol, has good properties. If you run it for polylogarithmically many rounds, and it gives you good properties with overwhelming probability. So what will happen if you only run it for constant time? If you only run it for constant time, it will have good properties with constant probability. But this is Not good because it does not solve consensus. You need those good properties with overwhelming probability. And this is not good in the single chain setting because you have no way to check if you have agreement of validity. So if we go to the parallel chain setting, then we get some advantages. So what are the advantages here? So that is we have m blockchains, and they are sufficiently large and they are mutually independent, which means that if you have good properties on a single chain with probability beta, then you will have good properties on beta fraction of the chains. Why is this good? Why is this good? We call it a phase. So it's like in each phase, a phase consists of constantly many rounds. We run parallel blockchains. And what we can do is that it is already very good for validity. Because if all the parties start unanimously, then you will see that sufficiently many parallel blockchains give you the same output. But this is not good for agreement for a single phase. That's because for a single phase, even if the corrupted parties, they dominate on one single chain, if the input configuration is like half of the ones and half of the zeros, then they might be able to dominate the majority output, even if they can only dominate one single chain. So the way that we solve this problem is that we will use phases to emulate the rounds in the classical king consensus protocol. And it's like we run blockchains in each phases, and each phase emulates one round in the classical protocol. And we have the problem here that in the classical protocol, you have round by round very naturally. So how do you run the phase on parallel blockchains to say one phase by another? You need some additional considerations. I'm not going to present it, but it's a bit complicated, but we managed it in our paper. And the conclusion is that with parallel blockchains, we are still able to run phases one by one, and they are independent. And in each phase, a constant fraction of the chains will have good properties. So go back to this protocol. We almost have all the things. We can check if parties start unanimously, and we can let them decide if sufficiently many blockchains have the same output. The only thing that we want to do, we cannot do right now, is that we can't do oblivious king election. So in the classical protocol, this is the most important part. This is the most complicated part because you have to design a very elaborated protocol like verifiable secret sharing or some other things. But here we want to do it using only random oracle. And presumably this should be the most tricky part. But how do we do that using only random oracles? And our answer is that we don't need to do anything we already have it. So this is our approach. The approach is that if you want to do oblivious king election, you don't need to do anything. You just deterministically fix a chain as a king, which means that, for example, we fix the first chain as a king. If the parties are confused, then they take a look at what the first chain outputs and replace their input with what the king chain tells them. So why this is good, why this is already sufficient for consensus, because we use M for one proof of work to bind all the mining procedures. They are independent. Although the adversary can win on a constant fraction of the chance, he has no way to choose which chain he's going to win. So even if we deterministically set the first chain as a king chain, the adversary can still win it only with constant probability, which means that with constant probability, this king chain will be a chain which we obliviously have agreement and validity, which is already sufficient to solve the consensus protocol. And to sum up, what we do here is that we run parallel blockchains using M for one proof of work and divide them into phases. And we use one phase to emulate one round in the randomizer king consensus protocol. And the final thing that we want to do is that we should trick the way that we do oblivious king election by deterministically set the first chain as the king chain. And that's for the consensus part. And for the rest of the time, I also want to give a brief overview of the distributed ledger. I will only highlight the technical obstacles here and how we managed to solve them. So the problem here is that with the expected constant time protocols, parties will terminate non-simultaneously. So if you want to run a ledger that is a sequential composition, sorry, there's a typo here, that's a sequential composition. If you want to have a ledger by sequential composing the consensus protocols, then you need to handle the non-simultaneous start for the second and the later invocations. Which means that we have to handle how to start how to start for the second invocation. And naively, this will take you polylogarithmic time, which we don't like. So which means that we need a sequential composition, which we do it by the Braha termination and the superface expansion. I'm not going to talk about the details, but the high-level idea is that we must expand the face, which means that a superface consists of some normal faces, and the protocol in the second and later invocations, they will proceed with these superfaces. And we design a way for these superfaces to converge, even if we do not start, even if we are still mining the parallel blockchains. And another thing that I want to highlight here is that for the distributed ledger protocols, it obviously it needs multi-valued consensus, and our chain king consensus is already a multi-valued consensus protocol. But the problem here is that in validity, in multi-valued consensus, validity is too weak to give you liveness. So what we can do here, is that in our ledger consensus protocol, we do a small tweak on how we decide the output of the king chain. So it's like when all the honest parties they are confused, they refer to the king chain, and they will output the input message with the minimum proof of work as the output of the king chain. So what's the security guarantees here? So with constant probability, the king chain will be a good chain, which means parties have a common view. And with constant probability, the output, the input message with the minimum hash value will be produced by the honest parties, and which means that with constant probability on the king chain, it will be output value by the honest parties. And this gives you liveness in expected constant time. So we have this round-preserving sequential composition of the chain king consensus, and also we have this minimum output rule, which gives us fast state machine replication. And our conclusion is that in the same setting as Bitcoin, we can confirm all the transactions in expected constant time. And this improves all the previous works, which has good accelerations for the non-conflicting transactions, but they degrade to the normal case like Bitcoin in the conflicting ones. So we get the acceleration for all the transactions. And to quickly sum up, so what we do here in this paper is that we do the consensus in the peer-to-peer network, public setup, proof of work setting, and we give a new protocol that terminates in expected constant time. Yeah, and that is, and we do it with synchronized clocks and static participation, but we will very soon post a paper on how to do it with dynamic participation and how to use it to synchronize parties' clocks. Yeah, and that's all. Thank you.
We have time for questions. Please come to the front. So I have a question regarding parties that join the protocol execution. So is it difficult for them to
join?
Do you support late joiners that then?
We design a bootstrapping way to join the ledger.
Okay.
So you only need to observe the execution for some constantly many rounds, and then you can bootstrap your blockchain. Although your blockchain will not be completely the same as the others, but the state for the consensus will be the same.
Okay.
Yeah.
We have a question.
So I have a question about. Okay, I think you already mentioned that it doesn't work for dynamic participation.
Yes.
But okay, so if you would run this in a model where parties are sleepy, right? Mm-hmm. So would it fail, or?
Our current construction is designed for the static case only, where we do not have a difficulty adjustment, which means that it will fail. So if we want to run it with dynamic participation, then you need to have a way to reactively adjust the mining difficulty, and we are trying to do that.
No, but I'm not talking about dynamic participation. Like, assume you have a static set of participants.
Yes.
Some of them might fall asleep from time to time, right? So
yeah.
I mean, would it still work?
It will work as long as not too many parties sleep.
So it's still a subquadratic protocol in terms of communication complexity, then, or?
I didn't think about the communication complexity of this protocol, but it should be this in terms of the. It should be only depend on the security parameter.
Okay, but there's this sleepy consensus protocol by Pass and Xi, and they essentially replace the proofs of work using VRFs.
Okay.
Right. I mean, plus or minus. So I wonder, could you you do it also from just using BRFs? But,
I have not yet considered this problem, sorry.
okay, yeah. So it's,
Yeah.
So any other questions? Otherwise, let's thank the speaker again. And this also concludes this session. So thanks a lot, you, and thanks a lot, Søren, for these great talks, and a lot of fun at the RAMP session, which is happening soon. Yeah. Thanks a lot.